In the first part of this video lecture, we have learned how to get the span of a given set of vectors. We have learned that the span can be obtained by simply taking the linear combinations of given vectors. Now, sometimes it can happen that a set is too big that if you remove some vectors from it, the span does not change at all. This type of vectors are what we call as the redundant vectors. So in the second part of this video lesson, we will study a condition where it determines whether a given set has a redundant vector or not. Because according to the previous video lesson, we wanted to produce a spanning set for a vector space that is as small as possible. Okay? So let's now going to define linear independence. A set of vectors S containing v1 up to vn is said to be linearly dependent. So I am defining dependent here, or sometimes I abbreviate by LD. If you can find scalars a1, a2 up to an, not all of which are 0. So in other words, not all of these are 0. But even though these are not all 0, the linear combination on the left-hand side of the equation is 0. So when can we say that the set of vectors is linearly dependent? If it is possible that this linear combination is 0, even though we don't make every AI 0. As you can observe, as you may have observed, no, if you just set AIs to be 0 for all I, then of course, this is trivially 0. But that is not the interesting case. The interesting case is when the AIs are not all zeros, but then this linear combination is 0. When that happens, we say that this set is linearly dependent. If the only way for this equation to be 0 to just set all of these AIs to 0, we say that the set S is linearly independent. As you can tell, that is the negation of what we mean by being linearly dependent. Okay? So what we mean by linear independence actually is the following. So we can say that S is linearly independent if and only if whenever this equation holds, whenever this linear combination is trivial, it must follow that each of these coefficients, or scalars are 0 or is 0. Now, one of the common errors of students in linear algebra when a teacher or when an exercise says, show that S is linearly independent, normally a student argues like this. Let A1 be 0, A2 be 0, A3 be 0, and so on. Therefore, A1 V1 plus A2 V2 plus A3 V3 and so on equals 0. Of course, that will hold, whether the set is dependent or not. The proper way to prove that a given set is independent is to start by assuming that this equation holds. Eventually, you have to force or you have to imply that the scalars a1, a2 up to an are all 0. In other words, the scalars being 0 should be an implication, not an assumption. So let me clarify that. Okay? Okay. So let's consider this set of vectors, v1, v2, and v3. These are vectors from R4 because there are 4 coordinates. 1, right? Now, as you can tell, it's not really easy to tell whether a given set is dependent or not, but I'm going to show this for you right here. No, I did some computations beforehand. No, I know that this set is linearly dependent. When you say dependent, it is possible to get scalars, not all zero, so that the linear combination is zero. Or can we make this zero? Or can we make linear combinations of this zero even without making all of the scalars zero? In fact, that's possible. Look at this equation. 1 times v1 plus 2 times v2 plus negative 1 times v3. You can check that that makes the sum equal to 0. Although these things are not all 0. When you say that not all are 0, it is not the same as all are not 0. They are different things. When you say all are not 0, each one in the set is not 0. But when we say not all 0, it is possible that there is a 0 in the set, but there must be at least one that is not 0. I hope that you recognize the difference. Second example, do you remember these vectors e1, e2, and e3 from R3? In this case, F3, to be more general, where F is a... We claim that this set of vectors is linearly independent this time. How do we show independence? We normally do the following. Remember, the fact that the scalars are all zero should be an implication. So we assume or we suppose that this linear combination is zero. We wanted to show here that each of the AIs is zero. But when you simplify the left-hand side, when one simplifies the left-hand side, you get the following. And therefore, that implies A1, A2, and A3 to be all zero. In other words, the linear combination of these three vectors can only be zero, the zero vector, if you set all the scalars to zero. So there's no other way for the combination to be zero but to make all the scalars zero. That means independence, linear independence, Li. That is different from, that's the opposite of being linearly dependent. Okay? As a quick generalization, if you let Ei be the n tuple point with n coordinates, where every coordinate is 0 but a 1 on the I position, the vector is called E sub I in linear algebra. Okay? And if you collect all the E sub i's, I from 1 to n, this set is linearly independent in Fn over F. Let's look at these examples. The vectors v1, 1i, v2, I minus 1 in C2. What do you mean by C2? C2 is a set of points with two coordinates where every coordinate is a complex number. So we allow complex numbers, or we allow imaginary numbers to be coordinates in this case. So just like this, no? V1 is 1i, V2 is I minus 1. It can be shown that, well, this is linearly dependent over C. When I say over C, the scalars are complex numbers. Okay? Because when you try to multiply I to v1 and multiply negative 1 to v2, you get the following computation. As you can see, the resulting sum or combination is the zero vector in C2. So you can see the scalars I and minus 1 are not all 0, but then the combination is 0. So linearly dependent over C. But look at this. Using the same set of vectors, but changing the scalars to something else, let's say R. This set is now linearly independent. I'm so sorry. There's a correction again, once again. This time, this set is linearly independent over R. What do you mean by over R? Now, the scalars that are allowed to be multiplied to V1 and V2 are just real numbers. So if we just force this to be real numbers, no? Yeah. For example, if you suppose that A1 and A2 are real numbers such that This is true. They are real numbers. That would mean the following, right? Because these are real numbers, for this to be 0, we need A1 and A2 to be both 0, proving that this set is linearly independent over R, although it is linearly dependent over C. So the linear dependence does not depend on the vector space alone. It also depends on the field of scalars. You understand me? Hope that is clear. Sometimes when you change the set of scalars, the dependence gone. Okay? That's the idea. Alright, generally, how do we know whether a given set is dependent or not? So that's the next question. Normally, when I wanted to know if given set of vectors is independent or not, I just do the following trick. I just suppose I write this linear combination. I suppose that A1, 1, 2, minus 1 plus A2 minus 4, 1, 1 plus A3 minus 2, 5, negative 1 equals 0, 0, 0. Okay? So our goal is to find all the possible values of A1 and A2 and A3 so that this is true. If the only possible values that satisfies this equation is to just make all of these 0, then the conclusion is that the set is linearly independent. But if there is a non-trivial choice for A1, A2, and A3, no, then what? We get linear dependence. So let's look at this example. So let's continue. We simplify the left-hand side. We get A1 minus 4A2 minus 2A3, comma, 2A1 plus 2 plus 5A3, comma, third coordinates, minus A1 plus A2 minus A3, then that equals 0, 0, 0. Weighting coefficients, we get the following linear system. But this time, what type of linear system was produced? It produces what we call as a homogeneous linear system because the constants on the right are all zeros. Do you notice that? Do you remember from a previous old lesson that if you have a homogeneous linear system, it always has a solution, which is the trivial solution or the zero solution. But for a homogeneous linear system, we are interested whether there is a non-trivial solution. Huh? So, in this context, the existence of non-trivial solution implies that this set is linearly dependent. Okay? If there's a non-trivial solution, then the system, or I mean the set of vectors is linearly dependent. You can get AIs, not all of which are zeros. No? That makes the equation true or the combination trivial. If the only solution is the trivial solution, that means, or that translates to linear independence. So let's proceed by performing Gauss Jordan once again. So as you can notice, determining whether a set is dependent or not amounts to again doing RREF, like what I've told you. So let's use a calculator this time because we don't want to mess up with the time. We only have a limited time here. Okay, so let me type in the data. So our matrix A is 1, negative 4, minus 2, 0. Actually, you don't need to write the last column because they are just zeros. But for the sake that to show that there is a zero column, so let me just put it. Okay. So this is your augmented matrix. So we're going to get the RREF of this matrix. So here is the RREF. The RREF is 102.0.1.1.0.0.0.0.0. As you can see, just ignore the last. We can just ignore the last row, sorry, because they are just all zero. So you can just ignore. Therefore, encircling the pivots, so these are the pivots. This corresponds to the unknowns A1, A2, and A3. As you can see, A3 is free. So what do we have? We have infinitely many solutions. In fact, as a general rule, or the general formula for the solution, if we set A3 to be R because it's free, what is going to be A2? Looking at the second row, this translates to A2 plus A3 equals 0. Therefore, A2 is negative A3. But A3 is R. Therefore, A2 is minus R. If you now look at the first row, this translates to A1 plus 2A3 equals 0. If you're solving for A1, that means that's negative 2A3. Therefore, that's minus 2R. We only have one free variable. Therefore, this is the same as R times minus 2 minus 1, 1, where R is an arbitrary real number. So you can take any real number, R, and you can see all the solutions to this linear system are the vectors which are multiples of minus 2, minus 1, 1. For example, just set R to 1. We get the following non-trivial value. Don't set R to 0 because you will just be getting the trivial solution. But the fact that we have a non-zero solution, or a solution that is not the same as the zero vector, that means to say that this set is linearly dependent. Okay? That's the conclusion. So this set is linearly dependent. Let's try another one. So we have 0, 1, 1, 1, 0, 1, and 1, 1, 0. By the way, let's look at the following. As you can notice over here, the given vectors 1, 2, negative 1, negative 4, 1, 1, negative 2, 5, negative 1 are precisely the columns of this augmented matrix. So basically, to test whether a given set of vectors is linearly independent, you just place them in columns. Now, this is the reason why some authors or some teachers like to use the vertical form of a vector. Sometimes they write vector in the vertical position because when they translate to linear systems, they're actually in the vertical position like this. And then on the right, you just put zeros. Then just run RREF. If you get infinitely many solutions or if you get a free variable, then, well, you get a non-trivial solution. Because aside from the zero solution, you get another one. Okay? If the only solution is 0, or this transforms to something like the identity case, then you only have the 0 solution, therefore that's independent. Going over to the next example, we will still do the previous method, but this time take note that the scalars are now not real numbers. They are now coming from the binary field z sub 2 that contains only 0 and 1. Now, how does this 0 and 1 work? They work as usual, except whenever you have a 1 plus 1, you replace it by 0. So what you do now is you just place them in columns like this. And then we will run a Gauss-Jordan method. Unfortunately for this, we cannot put them into Scilab because the Scilab interprets things as real numbers. And these are not real numbers. Although there may be a code, no, that you can develop, but So let's work on this by hand. So first we need a pivot on the first row. So I will just interchange with the second row. For example, get 1 0 1 0 0 1 1 0 1 1 0. Okay, let's row interchange over there. Next, I wanted to, using this pivot, I wanted to zero that out. I would like to do the following. What's the negative of 1 in z sub 2? The negative of 1 in z sub 2 is just 1 because 1 plus 1 is 0. Okay? So, you just write here E311 instead. Or in other words, you just add the first row and the third row because 1 plus 1 is 0. But of course, we will not change the first and the second row. Only the third row will change. So we're going to add the third row to the first row. 0 plus 0 is 0. 1 plus 1 is 0. 0 plus 0 is 0. As you can tell over here, as you can tell from here, the matrix is already in RREF. Okay? A1, A2, and A3. So the free variable is A3. How did I know it's not a leading variable? A1 and A2 are leading variables because the columns corresponding to them have pivots. So if we just set what A3 to R, what's going to be A2? Negative R. If we set A3 to R, what's going to be A1? That's minus R, right? Where R is an element of Z2. But Z2 only has 0 and 1. So basically, there are two solutions. What are the two solutions? When R is 0, when R is 0, and when R is 1. When R is 0, it's just a trivial solution. When R is 1, you get a minus 1, minus 1, 1. But minus 1, minus 1, 1 is what? Minus 1, minus 1, 1 is just the same as 1, 1, 1. In Z sub 2, not in Z sub 2, the negative of 1 is just 1 because 1 plus 1 is 0. So because there is a non-trivial solution, which is 1, 1, 1, maybe you can just, 1, 1, 1 means this. You multiply a 1 on each and then add them, you must get the trivial solution. A trivial, the 0 vector. Because not all of these are 0, so again, the set is LD, linearly dependent, because there is a solution aside from the 0 vector. How about these polynomials of degree at most 2? Is this set dependent or independent? So again, let's do the following. We suppose that a1 x squared plus 1 plus a2 x plus 1 plus a3 times x equals the 0 polynomial. The 0 polynomial, take note, is 0x squared plus 0x plus 0. If you simplify the left-hand side, you get a1x squared, okay? The x terms to a2 plus a3. The constant terms are a1 plus a. Okay. And then equating coefficients, we get following. A1 equals 0. Comparing the x squareds. Comparing the x's, get a2 plus a3 equals 0. And if we compare the constants, get a1 plus a2 equals 0. So this is your linear system that's you're going to solve. But as you can see here, no need to actually run the RREF or the Gauss-Jordan method. Because what? Because from the first equation, A1 is 0. If you substitute 0 here, you conclude that A2 is 0. And when A2 is 0 over here, you get A3 is 0. So by just using observation, we can observe that A1, A2, and A3 all 0. Therefore, the set of polynomials x squared plus 1 is linearly independent over the real number. Okay? Get what I mean to say? There are just some few remarks that I would like you to always know. Number one, if you have a collection of vectors and one of these is 0, I mean something in the list is the 0 vector, you space, then automatic this set is linearly dependent. Why? Let's just say without loss of generality that uh, V1 is the one that is 0. Okay? So in this case, if V1 is 0, no matter what scalar I put on V1, let's say I just put a 1, I still get the 0. And even when I put a 0 here on V2, then 0 on Vn, no matter what these vectors are, this is always, I'm sorry, yeah, this always equals the 0 vector. And as you can tell, this collection of scalars are not all 0 because one of them is not 0, namely the scalar 1. So, if one of the vectors in a collection or in a set is 0, the conclusion is that it's linearly dependent. Okay? Second remark, if you only have one vector in the set and this set is not 0, then automatic, that means that S linearly independent. Why? If you only have one vector, how should the linear combination look like? It will just look like as follows. It will just look like A times V. And if this linear combination is 0, remember from a previous theorem, if the product of a scalar and a vector is 0, then either the scalar is 0 or the vector itself is 0. 0 vector. But by assumption, V is not the 0 vector. Okay? If this does not hold, therefore, the conclusion is that A is 0. So the only way for this to happen is to just set A to 0 because V is not 0. Therefore, that means linear independence for the set S. Last in the list, if you get a set S, V1 up to Vn, and it has a linearly dependent subset, I mean, a portion of S is linearly dependent or known to be linearly dependent, then S itself is going to be linearly dependent. So in other words, if you have a linearly dependent set, you add more vectors to it, the resulting set is still linearly dependent. You understand? Okay. Why am I asking? As if you're going to answer. Okay, so let's see why. Let's say t is some integer between 1 and n, and suppose that, or let's not use suppose, let's use assume that, or let's just write assume without loss of generality that the subset, let's say that the subset that is linearly dependent is the subset from V1 up to Vt. So here it's like as if v1 and up to vt is somewhere here, and then we run over vt plus 1 up to like that. So let's assume without loss of generality that the subset V containing V1 up to Vt is linearly dependent. What will happen? By definition, then there are scalars A1 up to 80 from F, magic phrase, not all of which are 0, but A1 V1, A2 V2, A3 VT is 0. Okay? So what will happen now? So if it happens to be that in that if that case happens as a result is that I can just extend this sum into the following. I can just add 0 Vt plus 1, 0 Vt plus 2, and all zeros at the end till I get a 0. As you can tell, these scalars, even though I put zeros there, no, these scalars are still not all of which are zeros, because not all of A1 up to 80 are zeros, right? Therefore, that case means that the set V1 to Vt, including Vt plus 1 up to Vn, is linearly, because I was able to make a combination equal to 0 even without using all zeros. That's the proof. We now have come to, well, almost the answer to the question in the previous video. We ask, um, what did we ask? We asked, how do we know in advance whether given set has a redundant vector or not? Again, a redundant vector is a vector that simply falls in the span of the others in the set. It's called redundant because upon its removal, the span will not change. Okay? It turned out that if you have a set of non-zero vectors, we don't want 0 here because we don't want, because if one of these is 0, we also already have a conclusion. Dependent. No? So assuming that these vectors are not 0, then according to the theorem, S is linearly dependent precisely when there is a redundant vector. That is, there is some index j greater than or equal to 2, such that p sub j simply falls in the span of the preceding vectors v1 up to vj minus. Remember this property, if a vector has this property, remove it from the set, it will not change the span. Therefore, the moment that you know that the set is linearly dependent, you know that there is a redundant vector there. Okay? And because this is an if and only if statement, if your set is linearly independent, what does that tell? It tells you that an independent set cannot have a redundant. Okay? So let's write a proof to this very important property of theorem. Because this is an if and only if theorem, again, there are two parts in the proof. So let's assume that S is linearly dependent. We're going to prove that there is some index j greater than or equal to 2, so that Vj is in the span of the preceding vectors. Because S is linearly dependent, we can select scalars, not all of which are zeros, such that this linear combination is trivial, although these scalars are not all zero. So that I mean, that's the privilege that we have whenever we say S is linearly dependent. We can select these scalars to be not all zero, yet the combination is zero. So, among the scalars that are not all zero, we're going to pick the last one. I mean, among all the AIs here that are not zero, uh, one of these ones have the largest index. One of those which are not zeros has the largest index. I mean, the last one. So if you let J be the largest index so that AJ is not zero, meaning the last AI, so that AI is not zero, what will happen? It happens that all the AIs, so that I is bigger than J, will all be zeros now. Because J is the last one to be non-zero. So all that follows from AJ will be zeros. First of all, J cannot be 1. You know why? Because if J is 1, all the AIs that comes after A1 will all be zeros. So equation 3 will just reduce to this funny equation, A1 V1 equals 0. But because A1 is not 0 by the definition of J, no? J is 1. If this product is 0, it forces V1 to be 0. But V1 cannot be 0, right? Right? I mean, it forces A1 to be 0 because V1 is not 0. But that cannot be the case, or that contradicts the fact that A1 is not 0. Therefore, J cannot be 1, and therefore J is greater than or equal to 2. Next, we show that Vj is in the span of the preceding vectors V1 up to Vj. When you look at the equation 3, once again, can be simplified to A1V1 plus A2V2 plus AJVJ because remember, AJ is the last one to be not 0. All that follows after it are zeros. If AJ is not 0, so what we do here in this equation, we just leave this term on the left-hand side. We put everything on the right, so we will have a minus sign. And then, because AJ is not 0, I can multiply the reciprocal or the multiplicative inverse of AJ on the left-hand side, solving V sub j. So here is how I solve V sub j. I put everything on the right and then multiply the multiplicative inverse of AJ to the left and get the following. As you can see over here, I was able to express V sub j as a linear combination, scalar V1, scalar V2, scalar Vj minus 1. I was able to express Vj as a linear combination of V1 up to Vj minus 1. And in fact, that proves the one direction of the theorem, or 50% of the theorem. To prove the converse, no? So we are now going back. Conversely, assume that there exists a j so that this is true. And because Vj is in the span of the preceding vectors, then you can write Vj precisely as a linear combination of V1 up to Vj minus 1. That implies, if you try to put this term on the right, it will be minus Vj, but minus Vj is minus 1 times Vj, right? Okay? And this is equal to 0 because nothing is left on the left. Alright. Now, no matter what the values of these Vi's, I from 1 up to j minus 1, because this is negative 1 and this is not 0, it tells us something about V1 up to Vj. It tells us that V1 up to Vj is linearly dependent because the last coefficient or the last scalar is negative 1 and that's not 0. So not all of the scalars are zeros, yet the combination is 0. So even when you extend it up to Vn from the remark number 3, no, we know that the resulting set is still linearly dependent. Therefore, S is linearly dependent. As you can tell, the proof of the converse is quicker than the proof of the forward direction. Okay? And we have the following as a corollary. Okay? A finite set of non-zero vectors is linearly dependent if and only if it has a redundant vector. I mean, this is just a restatement of the theorem actually. Alright? And remember, our definitions and the theorems cover much like the finite sets of vectors, no? What if we have an arbitrary set of vectors? Let's say you have an infinite set of vectors. So here's how we define independence. A subset S of V may be infinite, is independent if and only if every finite subset is linearly dependent in the sense of our previous definition. Otherwise, S is linearly dependent. I think I should put this in yellow. Okay? For example, the infinite set of monomials linearly independent. No? Why? Because if you take any finite subset of this, let's say I took 1x squared to the fifth, for example, I cannot write any of this as a linear combination of the others. In other words, none of this is redundant or none of these vectors lies in the span of the others. For example, can I write x to the fifth as a linear combination of 1 and x squared? I don't think so. I don't think that you can ever produce x to the fifth by doing combinations of linear combinations, I mean, of 1 and x squared, right? Even x squared. The span of 1 only contains all the constants. Span of 1 and x squared contains the polynomials of the form a plus bx squared. Right? In this span, you cannot find x to the fifth there. Therefore, this is linearly independent by the previous theorem. In fact, any subset of this, any finite subset of this is linearly dependent. Therefore, that is linearly independent. In the next lesson, we're going to do the following. If you're given a vector space V over F, we're trying to look at a spanning set of V that is as small as possible. And by small as possible, we mean a spanning set that has no redundant vectors. I mean, that is linearly independent. In linear algebra, we want to minimize sizes. So you want to find spanning set that is as small as possible with no redundant vectors that spans the given space. And such a set in linear algebra is called a basis for the space. That will be for the next lesson. See you again.